All right, so my video cut out in the last one unexpectedly, so I'm just going to pick up where I left off. I was talking about this example here. So we have not P implies Q, and based on the previous example, P implies Q is equivalent to not P or Q, which means this statement can be swapped out for this statement. Okay, now here's where I want to use De Morgan's law. Remember, De Morgan's law was a law that told us what to do if we have either a disjunction or a conjunction that we're taking the negation of. And in a certain sense, you can kind of think of it similar to how you do a distributive property. I can kind of distribute this, that's my son. We can distribute that negation in, which gives me not P. Now, when you do that, De Morgan's law says that this connective changes. So if it was a disjunction before, it's going to become a conjunction in this stage right here. And then I also have my negation hitting that Q, so not Q. Finally, what's the negation of a negation? If you have a true statement, the negation makes it false. But then if you take another negation, it's back to true again, which brings me back to the original statement. In other words, a negation of a negation causes those two negations to cancel out, and I have P and not Q. So this statement here is equivalent to the negation of a conditional. We're going to use that in the next two examples. So here it says determine the negation of the following statements. If I study all night, then I will pass my exam. Notice again, the word then is not showing up, but you can think of there being a then there. So here, study all night is the antecedent, so that's like P. Pass my exam, I will pass my exam, that's our consequent, that's Q. According to what we just did, the negation of this statement can be put in the form P and not Q. So P is I will study all night, or I will study all night. Okay. Our conjunction here is the word and, so I can write and. Then we need the negation of Q. So what is the negation of Q? The negation of Q is I will not pass my exam, and I will not pass my exam. You could also say I will fail my exam, since that's the only other case that can happen. If you don't pass, then you're automatically failing. And again, if you read this, you think about it, this does make sense as the negation of this. Anytime this is true, the statement up here, this will be false. And anytime this statement is true, this one will be false. Here's a second statement that's not in if-then form, but we can put it in if-then form. Every dog has 4 legs. So we can write this if an animal is a dog, then it has 4 legs. So what I'm doing is I'm not writing the negation yet. What I'm doing is rewriting this statement in if-then form so it's more clear what the antecedent and what the consequent are. And notice again, when you rewrite something in if-then form, sometimes you have to to make it work grammatically, you might have to insert new words. So notice every dog became if an animal is a dog. Even though the word animal never showed up in the original one, it's kind of one of the only ways to make sense of this in if-then form. So I can't say if a dog, then it has 4 legs. That's grammatically incorrect. Okay, so now that I've done this, what is my P and what is my Q? Well, an animal is a dog is P. It has 4 legs is Q. How do I then find the negation of this statement? Well, again, we use this statement that's equivalent to the negation of P implies Q. So P and not Q. P, an animal is a dog, that's P, and it does not have 4 legs. Okay? So again, if you think about this for a second, writing this in this form does make sense because we can think of this statement in another way. Remember, that's a universal quantifier. We talked about those in the previous section. We also talked about negations for universally quantified statements, which always involve an existential quantifier. So if I say every dog has 4 legs, the negation of this would be some dog, or a dog, that's an existential quantifier, a dog does not have 4 legs. And that's basically what this statement is saying in slightly different terms. Okay, so that's a little bit on conditionals. Now we're going to wrap this section up talking about what are called circuits, which is a way of analyzing compound statements using a diagram. And what we're doing is we're borrowing circuit diagrams from electronics. So it turns out that the study of symbolic logic is extremely closely related to the study of constructing electrical circuits, so much so that we can think of one in terms of the other oftentimes. And so here's how we do this. What we're going to do is take compound statements, and we're going to look at the component statements within those compound statements and represent them by switches. And in a circuit diagram, these little arrows are called switches. And if you notice, there's like these little nodes or these little dots here. You want to think of the dots that these switches are attached to as almost being like a hinge. So that switch can stay open the way that I have it written right here, or they can swing shut. We associate the position of those switches, and I mentioned this again on the next page, with whether the component statement is true or false. So in this case, all of these switches are open. Think of it as like an open door. In those cases, we're interpreting those component statements as false. But if I were to close those, if I were to swing this thing shut, then we interpret the shut switches or the closed switches as true. That's like a truth value of true for whichever component statement that appears in. Okay? Now, the idea in circuit diagrams is to determine whether a compound statement that's represented by one of these diagrams is either true or false, depending on the ability of a signal to pass from the left to the right. So here's an example. See this series circuit right here? Both of these switches are open. What would it take for an electrical signal to pass from this end of my circuit to this end? Well, I would need both of these switches to be closed in order for that to work. So this circuit or this compound statement will be true only if both P and Q are simultaneously true. Remember, only if those two switches are closed, because then I can close that path and send a signal from the left to the right. For that reason, this circuit diagram is equivalent to the conjunction P and Q, because remember, the conjunction is true only when P and Q are both simultaneously true. Okay? Compare that to over here what we call a parallel circuit. Series and parallel, those are both terms that are used in electronics when designing circuits. In this case, I'm starting on my left endpoint, and I want to send a signal from the left to the right. There's now 2 different paths that a signal could take to get from the left to the right. It could take this upper path, or it could take this lower path. Now, right now, both of these switches are open. So a signal cannot make it from here to here when both of these are open. But if I were to close one of them, say if I were to close Q, the signal couldn't get from the left to the right by taking this upper path, but it could take this lower path because that switch will have been closed. Similarly, if I didn't do anything with Q, if I left it open and closed P, the signal could get from the left to the right by taking this upper path. If I closed both of them, the signal could get from the left to right using either path. And so basically, what we conclude from that is that the compound statement that's represented by this circuit will be true anytime at least one of these two switches is closed, or in other words, anytime at least one of the two component statements is true. That's the same thing that happens in a disjunction, P or Q. Okay, so this circuit diagram is a representation of a conjunction. This circuit diagram is a representation of a disjunction. And what we're going to do is look at combinations of these things. Okay? So again, I kind of mentioned how to interpret a switch as being true or false, closed or open, that kind of a thing. Here's an example of a circuit that we want to analyze. And more specifically, I say simplify. What does it mean to simplify a circuit? Well, let's start by thinking about what this circuit would look like as a compound statement. Notice that there's a parallel circuit because it splits into two paths right here. So that tells me that there's going to be a conjunction or a disjunction somewhere. Okay? The top path is going to be the first component statement in my disjunction. The bottom path will be the second statement in my disjunction. So what is the top path though? Even though this is a parallel circuit to begin with, both paths lead us to series circuits, one switch followed by another. So the first one is the series P and Q. Remember, series represent conjunctions like this. The bottom path looks like it's P and R. Okay, so this circuit represents this compound statement. Now, when we say simplify a circuit, what we're trying to do is write this circuit in such a way that is easier or simpler looking, easier to analyze because there's less going on. And the way that we do that is we use equivalent statements to simplify this compound statement. I didn't type out all of the equivalent statements, but they are in your book. And I'm going to show you in the book where they show up. Let me kind of pick this up and move this. So right here, this is page 110 in your book. You have this list of equivalent statements that we can use to simplify circuits. And the idea is to take statements of one particular type and swap them out for one that's a simpler type. So what do we have in our example? We have this second one right here. We have a disjunction where both component statements are conjunctions. Okay? This, you can use truth tables to show this, is equivalent to this simpler statement, P and Q or R. And so I'm going to rewrite my compound statement that way. Okay, let me put this back up here. All right. So this is equal to P and Q or R. All right. So let's think of what that would look like as a as a circuit diagram. Well, we have a conjunction, which means we need a series circuit to begin with. We're going to start with P. And again, in these circuit diagrams, the switches are always open by default, and we just kind of imagine closing them if we want to think about different combinations of truth values for our component statements. So it's a series circuit to begin with, so I should continue from P without diverging into a different path right away. But then what should the next statement look like? Well, the next statement is a compound statement in its own right, and that statement is a disjunction. So at this point, we should split off into a parallel circuit like this. One of my paths will have Q and the other path will have R. Okay? All right. This circuit is a little simpler than this one because if you notice, only 3 component statements have to be written here, so there's only 3 switches to consider compared to the 4 switches here. And if you think about it, it kind of makes sense logically why this would be the case. Because P is showing up as 2 different switches here, if P is true, then we have to close both switches simultaneously. If P is false, then we have to open them both simultaneously. So basically, the position of these 2 switches always have to be the same. Why do we even need 2 switches to represent that? We don't. We can consolidate them into a single switch because the overall effect is exactly the same. Okay? So that's how we simplify circuits. There's more complicated examples that we could consider, and you'll do some examples or some problems in the homework for that. Last thing I want to do is draw a circuit from scratch. So here's a compound statement, and we want to represent this as a circuit. If you notice, this one has a conditional in it, and nowhere did we write, either here or on the previous page, what the circuit for a conditional should look like. But the key to this is to remember the equivalence between these two statements. P implies Q is equivalent to not P or Q. Okay? Remember, let me find that example again. We showed that here, that those two statements are equivalent. And by rewriting the conditional this way, we can now see this disjunction and think, okay, that's going to become a parallel circuit in my diagram. So I want to rewrite this statement as a compound statement where the conditional is not showing up anymore. So how do I do that? Well, the way this should be written is not P, except instead of P for my antecedent, I have a more complicated statement. So this thing is the same, actually let me write it like this. Not P and Q implies R is the same thing as the negation of my first statement. So the negation of not P and Q, or my consequent. That's using the same result that we have here, but with this more complicated thing. Okay, now this is a little bit messy as is, and I want to see if I can write this in a slightly simpler way. So what I'm going to do is use De Morgan's law to handle this negation out here. We've done an example with De Morgan's law in this section already. So remember, you can think of distributing this negation in, and as we've seen, once the negation hits this first statement, you have the negation of a negation, and those two things cancel each other out. So I get P. The conjunction becomes a disjunction. That's part of De Morgan's law. And then I take the negation of my second statement as well. So not Q or R. Okay? Now, I'm leaving these in parentheses just because I have more than one disjunction happening here, and I want to make it clear which one we're doing first. So now to the circuit. How do we construct this circuit? Well, from the very beginning, the very first thing that I have is a disjunction. And so I need to write that disjunction, P or not Q. Okay, so P. Now, what do you do with a negation? Well, the not Q is just its own switch, not Q. We don't do anything fancy with our circuits in this case. Okay? All right. Now, we should have something that looks like this. This represents the disjunction in parentheses. Now I have another disjunction, or R. How do I handle that? Well, remember, this larger conjunction on the outside is basically saying I need a parallel circuit where this shows up on one of my paths and this shows up on my other path. And I already drew this parallel circuit. It turns out it's going to be easier to go back to draw this next parallel circuit. So I'm actually going to start working from my left instead of my right here and do this. Like that. Okay, then I can join these two up and finish that up. Okay, so really, even though I did the thing in parentheses first, as you go from left to right, the very first split in this circuit, the very first part that becomes parallel is this disjunction right here. So we have this path or this path. Again, that's this path or this path. And then when I get to, when I send a signal along this first path, it splits again into another disjunction. So this is the circuit that would represent this guy right here. But again, going back to what we did in the beginning, we were starting with coming up with a circuit diagram for a conditional, and we had to start by using this equivalence that we established earlier. turn it into a disjunction so that you know whether you're working with a parallel circuit or a series circuit. Okay, that's going to wrap it up for section 3.3.